Hey, how's it going, guys? So here we are back again at the Python BACnet playground, and I'll just give you some updates here for where we are with our fault detection application with Python. Yeah, it's pretty cool. It's coming together, kind of neat. Got a lot of cool things to show you here. Yeah, so I'm using Cursor quite a bit to make this dashboard. I have to keep track of my API usage, but Cursor has been very helpful. Just like where to find this code if you want to try it out. Yeah, so this is the GitHub for the Python BACnet playground. We've covered a lot of ground here so far, and who knows, maybe this will just keep on going forever, and it'll just be millions of, not millions, but just dozens or dozen, we're past a dozen of just vibe coding applications, and eventually it can be something turned into useful context. So if someone wants to try this out, they can create their own private GitHub repo and maybe create some kind of a similar application or something inspired by it. So please look me up if you need help with that. I'm actually looking for freelance, at the time of writing this, I'm looking for freelance work. So if something like this is interesting to you, of being able to use Python for your fault detection purposes of your HVAC data, and I have everything, it's free so far, which I'll explain. It's a little bit more involved than probably using like a canned or some kind of professional service out there, but a lot of analysts are already familiar with Python, and if you need a little bit of help with like the BACnet side, that's also in Python. Buried deep in like some of the beginner levels of like how to use Python IoT applications in the edge environment. We've covered a lot of ground in there. So yeah, without like further ado, let's get into this. So we're using Ansible. We're using AWS IoT Core, like a cloud pipeline, I should say. So all of the features where we're sending data across the internet, MQTT secure, that's something all handled by AWS IoT Core. So it's kind of cool. We got to take advantage of AWS and all it has to offer, as well as the database, the Dynamo database on AWS, Lambda functions in AWS, so we can write custom Python code, and also I'm hosting a web application from a Lambda function. So this is all broken down with Ansible playbooks, which we should cover in more detail a little bit later. And then we'll also enhance some of these BACnet. So this is Python code that would live in the edge environment. So this is mostly what we've been studying on this BACnet playground, is like how to interact with building automation system BACnet devices. So that part is covered. So there's just so much going on in the AWS side for hosting the web app and fault detection functions. This is also making the BACnet side look easy, but there's a lot going on here, so ton to cover here. Check out the earlier videos. I'm just testing this out with on a Raspberry Pi with a one-wire digital temperature sensor, where I enabled the GPIO on the Raspberry Pi to read in the temperature sensor value, and there's a resistor on a breadboard. So how to basically get that spun up, and then we're also sampling the hardware temperature sensor value, and then using a small BACnet server. So we have a BACnet application. We've been using this BACnet scan tool quite a bit, and this quite a bit here. So. And then once we'll use Ansible, I'll probably keep this on the test bench. So this is like the BACnet data being served from the Raspberry Pi GPIO. I have this temp sensor installed by the air conditioning vent, so it reads kind of cold. My little office, you can see behind me, is just a really crappy residential split system, so it's not a real HVAC system, but it's coming. So I have permission to install this, get data flowing in a live HVAC system, which I'll explain in a second. So basically all this is here on the internet, and then what I want to get into is kind of redefining some of these rules. So I do have another project in fault detection I've been talking about a lot called OpenFDD, which uses an analyst framework in Python called Pandas, and very popular in data science. Modern data science probably uses Pandas to create like the data frame. It's like a big Excel spreadsheet, if you can imagine it in your head. But this is actually just raw Python algorithms that I'm using at the moment, and I think it's kind of fun. I actually like it more, but I think eventually we'll get probably into using Pandas and NumPy, which is a math computing library in Python. But some of the stuff I'm doing, it's like we don't even need that yet. It's just really simple rule-based algorithms for so like I'm sampling getting historical batches of data from the Dynamo database, and then just doing like really easy based flatline sensor, max values per, like max rate of change per hour, bounds, high and low sensor values. So yeah, let me show you this a little bit. So these are just really basic single sensor fault detection algorithms, very computer science-ishy. And then like once we get into something more complicated, like we'll be looking at more mechanical based algorithms for like an air handling unit system. Like, is it economizing? Is it not economizing? And then also, running the same things across all the zone temp sensors. So it's coming. Okay, so we'll load some of these rules in a second, but this is kind of like what the code is looking like. In like the last video, we covered a little bit on some of these computer science theory going on here. So we're just like returning a value of true or false for each time step in the data. So it's really simplistic. I'm sure that there are PhD mechanical engineers out there, something where they might have a slightly different approach than a rule based on every time step that what I'm doing. But let's explain. Let's look at that in just a little bit later. Okay, so maybe just to start with, I am like on AWS, when you kind of get your instance, you get 100 free US dollars worth of credits, and I am using this part, I guess. Forgot about this. So I thought it's still completely free with my free credits, but if you wanted to spin something up, you do get a free web app that you can so like the HTML that I'll show you in a second, that cost you $20, I guess, but I am using it, haven't paid a dime yet. So yeah, and for some reason I think if someone would want to use this, it would just be their own portfolio of buildings. Like, I can't imagine this scaling out to millions of buildings, but let's say you're a sustainability manager for hospital network or a school district network, and you have maybe a dozen buildings, 2 dozen, like one single web app. I think that would be more than plenty if we start getting if we make the web app correctly. Okay, so I'm gonna get out of this. Maybe some of these earlier videos I can, I kind of demonstrated how I deploy this. So I kind of zip it on my Linux server and then upload all these files to AWS. And there's like all these configuration files for They call it SAM on AWS. SAM deploy, SAM first upload. A lot of like YAML files for how to configure it. So that's the AWS SAM stands for serverless architecture model. I think what happens behind the scenes is like these Lambda functions are mini virtual machines on the AWS cloud platform. So we just get this mini virtual machine. I think that's the way I'm looking at it. Okay, so we'll look at the web app in a second, and then I need to get some more rules on there, but so maybe I'll just duplicate this. Whoops. Okay, so like maybe also anyone wanting to do some of the computer science theory, look at the AI generated course daily mini challenges. I need to keep on doing this too, so just to carve out a teeny bit of time each day, like a lunch break, to practice computer science theory. There's even some stuff that you can get into past algorithms. You can get into advanced data structures, which is coming. This will be the next thing on this app here, we need a data model. Okay, so if you wanted to go actually look at this code, I keep on updating it every day. So this is the Ansible playbooks. So this is what are deployed to the Raspberry Pis. So I deploy all the Python code to the Raspberry Pis. There's only one Raspberry Pi with a GPIO sensor, but there'll be a virtual machine in a remote building that I'll be using Ansible to push code to as well. And then the cloud pipeline. So this is the fault detection Lambda function. And then these are just individual Python files that are running in the AWS side. So that's one Lambda function. And then this is also the data ingest. So this is actually, this Lambda function is logged into the MQTT topic that I have going for this project, and it puts the code into the database basically. And then the web one, this is the web. So there's quite a bit going on here, and there's even JavaScript and CSS, kind of like typical web app, dashboard, HTML, so that's all served out of here. So all the code is on the internet for people to prototype with, which I'm doing. And please look me up if you want to try this out. I would love to help out. And like people that want to do this professionally, please look me up. I have just some hourly rates, and anyone that's just like someone learning, just a single person not doing this professionally, just jump onto the Discord and start asking for help. Okay, so back in here, AWS Cloud, I have like an expression rule cookbook, which I was saying, so with 9 rules right now, this will grow into more advanced mechanical system faults. But for single sensors, like this GPIO, I think it's pretty good. Okay, so this is the dashboard. Zoom in just a teeny bit here. So these are current sensor readings, and the thing that's kind of cool is like if I do there's like a refresh, this will give you, I've noticed like 30-second latency in real time to getting data from the cloud, from the Raspberry Pi on my test bench here to AWS, and I think that's pretty sweet. It's been really fast, so it automatically refreshes here every 5 minutes, or you can set it to 10 seconds or whatever. You can view all these different options for history. I'm just doing a maximum of 7 days worth of data. So maybe we can, once I get this future building deployed here, maybe I can adjust that. Like having like a month's worth of data would be ideal. Like I think like what you want to do as a consultant is to like for your buildings is, I'm just kind of shooting from the hip here, is like run, build reports like once a month. And then what I'm doing here too is like there's tons of, so this is the sensor data. This is also, I've explained before, a JavaScript library called Plotly that's handling all this, that does all the heavy lifting. I love Plotly. And there's logs down here if there's errors on the back end. So this is on the back end. And then this is the temperature sensor values on my crappy little split system in my office. Yeah, the HVAC system is actually really poor here. But I think like what we're more playing around with is just basic fault detection on some kind of ambient zone temperature data. So there's also ability to do rolling averages. So and then you can even wire in this to the fault equation too. So you have the abilities to, for the backend, to calculate 1 minute, 5 minute, or 10 minute rolling averages. And then I'll show you in a second in the fault detection, you can actually base your fault detection rule on this rolling average data. Okay, so let's, then like what I'm experimenting with, this would be kind of getting into some analytical representation, is elapsed time of these faults. It's kind of worthless for this data, but so if I just select that, so I have like all of these sensor bounds fault, and then if we would have all these elapsed time right here, that's what I'm with the computer is equating it to 9 hours and 51 minutes. So it's not very, for this little piddly thing, it's not super useful, but there can be instances where this could be an energy calculation. So like let's say a piece of HVAC equipment is running longer than what it should be, or there's simultaneous heating and cooling. If you can log elapsed time in some more advanced mechanical fault, that's where the mechanical engineer can then estimate some unit of power perhaps, and then times it by time, and then you have kilowatts per hour, and then they can equate that to dollars, and then eventually to estimating what would it cost to fix that issue, and now you can do an ROI or an investment return. So that's like more of a mechanical kind of fault, but then we're kind of looking here just at like sensors, electronic faulting is what I'm mostly interested in, because I already know that my crappy little HVAC system in my office is not that good. So it's just a place for me to play around with equations. Okay, so like we're in the Vibe Code 12 app on this dashboard. So if someone wanted to use this concept idea, you would morph it into whatever it is on your own private GitHub. And please look me up if you want to help with that. So here's a tab. I'm just calling it Bake a Pie, because essentially what we do under the hood is we play around with Python code in the browser, but that's sent to the back end, and the AWS Lambda function crunches those numbers for each time step. So let's just see if we can do this kind of quick as possible. also have a dashboard here. So I'm going to show you this too. Okay, so like, so here we are. This is me on the Windows computer that I'm recording this video from. This is my retired desktop computer. It's kind of retired. It used to be a Windows computer until I needed a more powerful one, and then it's now just on my little Linux server on my test bench, and this is where I'm clone the Python BACnet playground, and I do everything from here. So this is my SSH here that I use cursor to orchestrate everything. So we build the Ansible playbooks through here, and then that sends Python code to the Raspberry Pi, and it also sets up systemd and everything. And then this will also be that I have this future building here, which maybe I'll even be able to do by next week, is start scraping data to AWS IoT Core via MQTT Secure on it's a medium-sized office, 2 stories. It actually kind of looks a lot like this schematic. There's a roof-mounted air handling unit, and there's probably about 20 to 30 VAV boxes inside of it. So I'll also use Ansible to push updates to here as well. And that'll also include everything that AWS IoT Core requires, such as the security files, the .pem, .key, which encrypts the data across the internet. But there's quite a few things we need to do to even be able to get to that point. So yeah, just to recap, there's 3 Lambda functions, and then across the internet, this would be a firewall on my little office, and then this would be a firewall on this person's office. And then I need to actually put a note here. I just thought of this, that when we use Ansible to push code to orchestrate this guy, this is a virtual machine, Ubuntu virtual machine, which I'll be running BACnet, which is on the same subnet as their train building automation system. So I need to connect this to a VPN called Tailscale. So my little server will be on Tailscale, and then this little virtual machine will also be on Tailscale. So I'll use Ansible to push those updates through SSH through here, and then when we send data MQTT Secure to AWS IoT Core, that's just right across the wide open internet, encrypted through TLS, MQTT Secure. And then we're also running the web app. So like when I'm dialing into this web app, we're using HTTP Secure across the internet to get into AWS IoT Core. Okay, so hopefully this makes sense. A lot more to go in here. So there's what I'm hoping to do tomorrow is we need to kind of start thinking towards a data model and then different topics. So this will be the Boss Pi, my test bench with a GPIO sensor. That'll be, I think it's MQTT topic, its own topic. And then this building will be its own topic. And then part of that topic, there's usually MQTT does building equipment sensor in a string for the topic. So that's probably coming tomorrow. But for now, let's just kind of still play around with the rules. So yeah, a lot to go on vibe coding this. Okay, so right now we have 4 rules. And then we have an expression rule cookbook. So this is actually some code here. I actually copied this and testing it. So what these do is we grab the last hours worth of data. So like if you watched yesterday's video, we were playing around with data so the data that we get to work with is a list, and it's nested dictionaries. So this function grabs an hour's worth of prior rows of those dictionaries, and then I iterate over those rows. And then what we're looking for is we'll calculate a spread. Let's see, so where was that? So the spread is, can't remember now. Okay, so it's just the min and max values. So right here. So like that'll just be, so in a flat line, if the sensor was truly flatlined, like there's something with electronics, it's stuck, or it's not communicating, something's wrong with it, happens once in a while, like there would be no spread in the data. So the max value found in the last hour would equal the minimum value. So and then we just have a tolerance of 1/10 of a degree Fahrenheit. So this is something I do have running. If I go down to flatline sensor, this is running in here. And then there's this, I'll actually have maybe I'll just copy this again. So let's just demonstrate this. So this is kind of fun. You can play around with the Python code. So then, so we get to, so that I have like 7 days worth of data, but we can test the Python code on this window right here. So I just have 2 hours. Yeah, keeping the rolling average, and then test. Check a box for verbose prints, test. And there's also something here too, like you can copy this and send it to the large language model as well. So like you could even do print spread. So this, I think that what this will do is for each row of data, so this is the spread calculation. It actually looks kind of odd. Like it almost looks like the same exact number. Okay, so maybe we could even chat with the AI. The only thing we can't really see is like the data. Okay, so we could do this. Let's just try this. Maybe I just want to print that guy. Maybe I'll just do spread. We should do an F string here. Whoops. Do some curly brackets. There's also a Python syntax checker right here too. Maybe just empty print statement just to keep things nice and tidy. Okay, so we might have a few things to keep up. Looks like there's some kind of like a little syntax error, but we'll have to fix that. Might be some little bug here that I have to, but it looks like it's actually calculating this spread. I think you get the point. So like, I might actually take note of this. Okay, so we did cover flatline sensor here. All right, so I just have a new tab open. I'm gonna keep this, open for my little notes to do some more updates to here. Okay, so maybe the next one is like, let's look at rate of change per minute per hour. Okay, so let's go to the BACnet Pi, and then let's do a rate of change per hour. So I might actually go into, that's rule number 2. Okay, so we have the same function here, evaluate. So we're actually just like calculating the rate of change per hour, maximum temp. Test the rule. Oops, okay, so we have to do a, this is our config parameter of 5. Okay, so we can get rid of that parameter, just type in a new one from our expression rule cookbook, and that'll be a value of 5 degrees per hour. We can type in 5.0. Verbose logging. Okay, so this is what we're calculating. So basically, like, we're throwing a fault if this would be greater than 5. So for each time step, we're looking back on an hour's worth of data and calculating that rate of change. And we don't have any faults. So like, if we really wanted to test this fault, so now we have lots of faults. And then what I can do here is write the values to the database. Okay, so now it's backfilling. It's backfilling the data on the database, Dynamo database on AWS. You can also see rolling averages and raw values here. Kind of cool. So like, you can also like when you're calculating your, we looked at this on yesterday's video, if you want to see rolling average data, you can do that too if you want to use that in your fault equation. Okay, so this is like, we caught up on our records, so 28 chunks of sample. It breaks it down in chunking to catch up on database records. Let's Let's just go back to the dashboard and then see how that looks. Okay, so we're refreshing now on the dashboard. And then we should have more rate of change per hour faults. See something that looks wrong. Okay, so this is actually wrong. This should be, did I put this on the wrong? I might have put this on the wrong one. Shoot, sorry guys. I put this on the wrong one. So this needs to be rate of change per hour. So that's what you can do. You can define your rules, and then once you test your rule, write it back to the database. Something right here that looks, I have to study this a little bit, how it grabs this V1 and V0. I think what it's doing, it's like, so it grabs an hour's worth of data, where on 10-second increments in that's a ton of data, and then it's calculating, it's just grabbing the first and last value, then it's taking the absolute value of that, and then it's using this, we're using in timestamp in milliseconds, we're back calculating like an hour in that, so that'll be delta temperature per hour. Okay, so let's go back to our dashboard. Refreshing. So this is a fun, really fun concept idea that I think could really be expanded upon. I'll probably be vibe coding with this for, because it's fun, you know. So, okay, so rate of change per hour, that's what we just updated. 10,000 hits, 32 hours in fault. That seems like a lot of time. So let's just look at some of the live data. So if this was an hour's worth of time, I have to think about that, like how it's calculating the rate of change per hour. If you would truly take the first and last value, but it's almost like we should be creating an average rate of change, I guess. Of course, an hour's time is kind of, there's a lot that can happen in an hour's time. Anyways, so like what's kind of cool behind this is like in here with the verbose words checks, this is where you can then like watch this, you can go then open up help with AI. How does this function look? Is it odd that I'm just gonna paste that in. I just like want to ask it. Just want to ask it something about here. this is the first and the last value in the array, right? For an hour's data. Okay, and then is it odd that we don't average the data to proper calculate rate of change for the past hour? Whatever. So I'm just like using the point of this exercise is like you can copy it into AI. And when you check the box for verbose prints, you can get every single row in your test data, and then it also plops into the here like kind of what you're doing, the config, and also the function, so all the Python code, and then AI gets to see all of the rows. So pretty cool. So I think I don't think anyone's doing this like where you can just copy paste, getting help with your fault detection rules with AI. Okay, so this is the first and last of the array. This is a valid net rate of change check in your report. That is why you see lines giving about 5 degrees, which exceeds your threshold. The thing you would do is not use raw data first, but if you're, okay, so like AI is recommending that we use the rolling average. So that's definitely something we have to use. And then it can even, this is not right. I don't think this is right. But I think we could even use that in here. So, whoops, that's the one that has the bug I gotta fix. But the point is, if we wanted to see that, I could just do a print row. Okay, so this is what each row of data has. And then we could be using the rolling average. So rolling average temp, which is this one, which would be the same. So I just can use this key rolling average temperature. So then we could even change this to instead of temp here, which is should be this. I should be able to just type in this. Sorry, I'm just checking one thing. Should be able to just type, use rolling average. Okay, so no errors. Let's update the database. So point is we can use AI to help us and even see some of the data. And the thing that's nice about it is like there's no AI that's built into the tool. There could be, but we're just kind of extracting it and outputting it manually, which is kind of nice. Like from a security perspective, like the IT person that you're scraping data, we're not using AI. We're not even using AI on AWS. We're just manually using it when we're tuning faults. Okay, so if we go back to our dashboard, this rate of change would be using average data. So it would be using the dashed purple line instead. So I really have to put some more thought into, just for fun. The only thing that would be really concerned with, maybe I'll even pan my camera here, is that like this, the breadboard, this could be really flaky. That I know that my HVAC is kind of crappy in my building, and my little cheap, sensor right here, I'm most concerned that the electronics are stable. I don't need like some advanced, mechanical fault, or really. I could maybe just put like a little bit more thought into, what would be the most appropriate fault for this application. But I think I might kind of just end it here. And curious, just for, what do you guys think? What kind of faults would you like to see? I mean, like I really want to do flatline sensor and then some kind of sensor out of bounds, where like the sensor should never, I put it on the exhaust of my computer that read up to like 90, 100 degrees almost, and then I put it in like a cup of ice water, so 40 and 90. So if it's reading outside of that range, I don't think I can get the sensor any warmer or colder with the things I have in my office. There's something wrong with electronics. I already know that my crappy little HVAC system is, I don't need to know anything more mechanical about that. So I think I'm just gonna go with like, maybe I'll delete out, maybe I'll just do this real quick. So let's delete this rule, rate of change per hour, goodbye. Okay, so now we're back into, or did I delete the wrong one? So this is flatline. Looks like there might be one more little bug on here. So I see a bug right now in the web app code where it's not updating. But, I'll kind of make some of these little fixes here and get something working. So I think like what I'm going to prove, okay, so I need to make a note on fixing that. I'll do that today. Actually, I don't need to do anything right here. What I want to do next, what I'm going to task Cursor to do is, maybe we can just type it right in here. So like, okay, so the next thing I'm going to say, like, I need to plan on deploying to a live building, HVAC in BACnet, where I need enhanced features to do a data model in Brick with external time series references, and this BACnet system has many devices, and I need the ability to plot many sensors at once for more advanced fault detection rules that could be mechanical based. We need a better MQTT building per system per sensor handling on the database and lambda function that handles listening to the topic. What else should we have? There's quite a few things in here. And to deploy via Ansible as needed. So all Linux Edge devices would have same code bases and AWS IoT Core PEM and key files. Then these edge devices need to be updated to be able to BACnet read sensor values. Okay, so like prior in this, we've done that. We've demoed that here. Say this is an example of BACnet read applications. And then also this one, I think. That's priority array. So this is BACnet ReadProperty. Please build out the driver for BACnet read purposes. Then also what I need to do too is so I'm just gonna, this is something I don't have yet. Let's see, give it this. This is like a BACnet scanning tool. Just other code bases like to discover BACnet and all points and devices. This script could be used to run on the Pi on the edge prior to discover the BACnet system and save data to a config file. That's a CSV where then user can modify and delete out CSV file rows for sensors they do not need scraped. So I'm going to plop that in. Please enhance the front end to use let's see, please enhance the front end to use brick data model for external time series references, where when data comes in on the MQTT topic, it should automatically hit the data model. And then the user can reference this in fault detection equations, where we can run rules across many sensors of the same type, etc., as defined in the data model. Please plan this in enhancement. Okay, this is a huge lift. So I might even put cursor into plan mode. And okay, let's do it. So this is another huge lift. Couple little bugs to fix, which is expected when you build out prototype some tools. There's going to be a couple little bugs even made with AI. But let's do this. So like we're vibe coding our own fault detection IoT pipeline and everything. So this is pretty cool. And then like one of the final enhancements to this will be doing some kind of like a basic login screen for the AWS web app. And yeah, we're getting there. So this is fun. Hope you guys are liking this. Please look me up if you're interested in, you need any help professionally or anything like that. I'm really interested in this topic and freelance work, and I'd love to be a part of your team. Until then, have a good weekend, guys. Talk to you later.